I just want to know opposite, hypotenuse, adjacent.
Opposite is the question mark.
Opposite is the question mark. Good job.
Hypotenuse is like the 4 meters.
Excellent.
And then the other one is the adjacent.
Okay, can you tell me a trig function that would bring together the sides of interest?
Sine 30.
Sine 30. Excellent. And what would that equal?
X over 4.
X over 4. There's no x over there, so I assume you mean this is x.
Yeah.
Okay, great, great. What's sine of 30?
Um,
Memorize it. It's a half. It's worth memorizing, okay? Yep. So what's that going to make x?
2.
2. Okay, so here's the first thing. Don't be screwed up by stuff that's that simple, guys. I don't want there to be problems. How high something is above the ground versus how far along a ramp it travels are going to be related to that angle. Don't get that mixed up and don't make that a problem. There's absolutely, at this point in time, no reason for you not to be able to move from one to the other. So if you're asked how high it is above the reference level, you know which one of these we're talking about. We're talking about the opposite side. If you're asked how far along the ramp it travels, then you're looking at the hypotenuse. But keep those in mind. They're not really a part of the physics at all. But it's those little geometry things that tend to kind of trip us up from time to time. And I'd prefer us not to get that stuff wrong because that's not the stuff that's worth getting wrong. Also, there's a bunch of you who jump to your calculator. It's about time. Sine 30 is a half. Get it in there. They use 30 degrees all the time. There's another one that gets used all the time, and that's 37 degrees. Do you know why? Because it's for a 3, 4, 5 triangle. And if you know about 3, 4, 5 triangles, you know that a 3, 4, 5 right triangle would be 3, 4, and 5. This is 37 degrees. They'll do this all the time because the sine is 3/5 and the cosine is 4/5. Everybody got it? These are worth memorizing. These are on your equation sheet as well. So the equation sheet has a small trig chart. They tend to use these angles because they want to make the geometry of our problems less of an issue. But there are going to be geometry portions. Also, how many of you checked to even see if your calculator was in degrees or radians? That's only about 2/3. I mean, that's 2/3 better than the other third, but check. Okay. So now that that's done, I will give you a minute to tell me how fast the box is going as it makes to the bottom if the coefficient of friction is 0. This was one of your test questions just the other day, right? The block of ice on the ramp? Okay. All right, Jaden, since you just had an epiphany, can you enlighten me? That's what we would have right here. Excellent. And if the block slides without friction, the total amount of energy in the system remains the same. Now, let's be honest, real world, very unlikely that's going to occur. Most systems are going to have friction. It's going to lose a little energy, so this is not ideal. The whole idea of them saying on your test that this is a piece of ice was to say that there's no friction. And that's great, but that means, too, that the box is going to make it from here down to here. Does it have any gravitational potential energy when it's at the bottom of the ramp? Not if you have chosen the ramp to be the reference level. So if this is your reference level, then when it's down there, it has no gravitational potential energy relative to the lowest point of the ramp. It only has gravitational potential energy because it's above the ramp when it's up here. If that energy can't go away, where does that energy go? Kinetic energy. At the bottom, it's going to have kinetic energy. So this is a one-step problem. We set the energy at one state equal to the energy at another state. We've done problems like this before. Just got to be reminded about them. So at this point, we're just talking about algebra. It's not particularly interesting, but it's worth at least making sure you've had a little bit of practice. So we can cancel out the m's. That happened all the time last year. And we have 1/2 v squared equals gh, or v equals the square root of 2gh. What's the height? 4 meters or 2 meters? 2. We want the height above the reference level. They don't have to give us that. And now you understand what you can do if they don't give us that, correct? Don't don't be led down a path to do the problem that's harder than it has to be. So yeah, we could have found the acceleration. The acceleration down the ramp comes from setting mg sine theta equal to ma. That would give us the acceleration. Now I want you to pay very close attention to this because you guys aren't particularly good with subtlety. This is the only force down the ramp because there's no friction. So I set the net force equal to ma. That means my acceleration is equal to mg sine theta. The initial velocity is 0. We're looking for final velocity, and we have that the displacement is 4, correct? So we'd use a motion equation for this. So if you did it forces, it's harder already. You can see that. That's assuming you got this right. And on our last test, we had a healthy selection of you guys who had cosine here. So we know that we don't always get this right. But I want you to pay attention. I want you to see something. A relationship that has all of those things in it would be v squared minus v naught squared equals 2a delta x. Good so far? Well, we'll cancel the m out. I didn't cancel the m out, so let's cancel that m out. So 2g sine theta times delta x. Do you guys see this right here? Are you paying real attention? Because if you were, you would know that a few seconds ago, we used that to figure out what the height was. Right? This is the hypotenuse. And we said the hypotenuse times the sine of the angle would give us the opposite side. Isn't that the hypotenuse times the sine of the angle? Which makes this side 2gh, and this side, v squared. Right. They're always going to work out to be the same. It's all built on the same foundation, the same information. Which one of these is easier to do? Okay, so we understand working with energy usually is going to be easier. And this assumes you can get the forces without doing a free body diagram. Forces tends to be harder, but forces can solve more complicated questions. It's always been the case. But now we're going to add to this, and that's what we're going to do today. Today, I don't want it to be that color. It's too bright. Let's go with this one, nice and dim. That way we can see the objects better. So we have our ramp again. Same ramp. Has a length of 4 meters, angle of 30 degrees. This time, there is a coefficient of kinetic friction and a coefficient of static friction. But this time, we're not going to put a block down. We're going to put something that will roll down to the bottom. In fact, I'm going to say there is sufficient friction for the object to roll. Now, I will remind you, last week you were asked to figure out the frictional force on something that's rolling. We know that that can be complicated because it involves dealing with both torque and dealing with forces. And although you can eventually get the acceleration and do the problem as we did last week, this can also be done as an energy question. Because just like a moment ago, this object has gravitational potential energy based on setting a reference level for the problem. I think an appropriate reference level for this problem will be right here. That's the lowest point that can be attained by the object as it rolls down the ramp. But here lies the difference. If the object rolls down the ramp and makes it to the bottom, it has two kinds of energy at the bottom based on what we talked about on Friday. We know it's going to have translational kinetic energy. We just did that. That's for the object that's sliding. Anytime an object's center of mass is changing position, and there's no fixed pivot point, an object will have translational kinetic energy. I'm not going to say that 10 times. I slowed down on purpose. So pick up them little pencils so you can take some notes. Anytime an object's center of mass changes position and the object doesn't have a fixed fulcrum, the object has translational kinetic energy. I know that I'm saying that very carefully, but you're going to see some situations in which the object's center of mass is moving, but it still only has rotational kinetic energy. Both of those have to be satisfied for an object to have translational kinetic energy. It has to have a fixed pivot point, and its center of mass has to be changing location. Two conditions. The word "and" in there is important. Circle it so that you know both things have to happen. This is worth studying. In addition, anytime an object is spinning, it will have rotational kinetic energy. So there are two kinds of kinetic energy: translational and rotational. So you got 2 points there, right? 1 point about when an object has translational kinetic energy, 1 point about when it has rotational kinetic energy. Third point, rolling is special. Rolling means that the translational and the rotational are connected. Rolling is special. This is not throwing a frisbee. This is not throwing a football. Rolling is special. Now, you guys, this part, I'd like you to have something in your notes about this. But before we do, let's do this question. I want to know how fast the disc is moving when it makes it to the bottom of the ramp. I want linear velocity at the bottom of the ramp. Okay, I want to show you how this is done. You guys ready to go? We clearly have gravitational potential energy because we're starting above the reference level. At the bottom, the condition is made for both translational and rotational kinetic energy. Although friction acts in this problem, friction doesn't do any work because the kind of friction involved is static. Static friction can't do work if the object is not slipping due to its contact with the surface. Kinetic friction can do work. It can take energy away. But static friction can't do work. Not like this. It's just keeping the system from sliding. So the amount of energy we have here has to equal the amount of energy we have here. Now, if you weren't here last week, and several of you weren't, we derived rotational kinetic energy. It's kind of exactly what you would expect. If you haven't been paying real close attention, every time we have a new rotational thing, replace the m with an I, and replace the velocity or the acceleration with the Greek letter for that. So in this case, 1/2 mv squared becomes 1/2 I omega squared. Translational kinetic energy stays the same, 1/2 mv squared, just like we just did. So at the top we have mgh. At the bottom we have 1/2 mv squared plus 1/2 I omega squared. What kind of shape did I say this was? I said it was a disk. So because we know it's a disk, we know it's going to have a certain moment of inertia. I didn't even give you the radius of the disk, and it's not going to matter. How often did we actually need the radius of something when we did these problems before? This is a circumstance in which it may not matter. So rolling problems, a lot of times, you won't need R unless you need to know how fast it's spinning. So let's do some of the obvious things that should make sense. Like, for example, let's put in the moment of inertia. So when you're looking at how this problem will be different than the problems we've done before, first step that's different, moment of inertia has to be used. Let's not forget, that's one of those things that you guys have been pretty good at. You'll notice I haven't put any numbers in. Didn't even tell you the mass of the ball. Or, I'm sorry, mass of the disc. Let's go to the next step. And I know I'm getting down towards the bottom here, so I'm going to scroll up a little bit. But it's rolling. Rolling is a condition. So we can use the condition that it's rolling. V equals omega times R. So we're going to use that condition here, just like we used it in the last case. And again, that goes right here. So our first thing was subbing in moment of inertia. Second thing, putting in the condition for rolling, the bridging formula. This puts it all in terms of V. Do note, R's are going to cancel here. Do you guys see it? Because I have R squared. And I have an R squared here. So, because of that, R cancels. Now I'll have 1/2 mv squared plus 1/2 times 1/2 m times v squared. All good so far? This is just simplification. All right, we did our substitution. There's going to be 2 substitutions for these problems. A moment of inertia and our bridging equation for rolling. But now we can just add things together. By the way, this is 1/2 times 1/2. What's that? 1/4. 1/4 times 1/2. I'm sorry, 1/4 plus 1/2. Can you do that in your head? Or do you need to add your fingers to that? It is 3/4. That's right. We are just doing simple algebra here. But we are going to cancel out the m's. Again, that happens a lot in these problems. I'm going to solve this for v. Look back at your notes. Is this faster or slower than the block sliding without friction? Not a hard question. Look back at your notes. It's like 1 page ago. What did you get for the answer for the block sliding down the ramp? That's right. So the block was the square root of 2gh. Is it clear 4/3 smaller than 2? Objects that roll are going to be traveling slower than objects that slide without friction. I keep saying that without friction because friction plays a wild card there. If there's friction, that changes it. But things that slide convert their energy from gravitational potential to just translational. Objects that roll have to split that energy into 2 different forms, translational and rotational. So objects that roll, because they split the energy, generally are going to be going slower because of that. They still conserve energy, though. All that energy is still there. In fact, if I asked you how much energy the system has at the bottom of the ramp, most of you will have difficulty coming up with mgh. But that's how much energy it has at the bottom. Even though at the bottom it's split up into 2 forms, it's got to be equal to how much energy it started with. Always. So in this case, we have a disk at the bottom. It's rolling slower than the same block would have slid if there was no friction. Now, you already know the answer to this. You saw it in front of you. But if we put a ring up there as opposed to a disk, what would win the race? The ring or the disk? Prove it. Put the ring up there at the top. Repeat this problem for a ring and tell me what the ring speed would be. This is straight up, just repeat yourself so you can get this into your brain. I mean, clearly even slower, right? 4/3 is bigger than 1. Now, I am going to actively try and trick you. Are you ready? And again, I'm telling you ahead of time, students will get tricked with this question. So I want to read this question. Let's say that I have the disc and the ring again. And a ramp that is long enough to accommodate what I'm about to give them. And let's say that I start the ring and the disc with the same velocity at the bottom. So let's say they both have a velocity of 5 meters per second. And they are both rolling. And let's also say that there is sufficient friction for them to stay rolling so they never slide. Which one goes higher up on the ramp? I want you to figure it out. If it's the same, fine. I don't think it will be. That's why I'm trying to trick you. A lot of you think it'll be the same. It won't be. So just reverse this question. They both have the same speed. How high up on the ramp do they go? Some of you will notice a shortcut here. Most of you shouldn't use the shortcut. You should start from scratch. What kind of energy do they have and what's going to be converted to? This is worth practicing. All right, a few of you are having some difficulty getting started. Difficulty getting started. Pick one of them right now, disc or ring. Ring, okay, so what kinds of energy does the ring have when it's rolling on the flat surface? Definitely has translational and has rotational, that's right. So it has two forms of kinetic energy. I'm just going to start from there. Those two forms lead me to 1/2 mv squared and 1/2 I omega squared. Now, you're going to do the same thing for the disk, but remember they have different moments of inertia. So you're trying to figure out how far along the ramp they go. I would start by just figuring out how high they make it above the ground. The one that makes it higher goes further along the ramp. If they make it to the same height, fine. But this is going to equal mgh when they come to rest on the ramp before they roll back down. Your job is to figure out how high each of them goes. I just worked it this way. Any problem with that? Isn't it all the same steps? I mean, I skipped the putting the the 1/2 mr squared in there, and oh wait, this were we doing the ring? Oops. If this is the ring, then I made a boo-boo. I did the disk. If it's the ring, then it's this. There, this is the ring. All right, a few of you don't believe me, so let's do what we did in the reverse. 1/2 mv squared plus 1/2 mr squared times v over r squared, which gives you 1/2 plus 1/2, which gives you 1. Cancel out the m's. Do the same thing for a disk, and you'll get 3v squared over 4g equals h. So yeah, I could put the 5 in there to see which one goes further, but can you tell which one goes further just from looking? So why does the ring go further up the ramp than the disk? Go ahead.
Since it starts with the same rotational velocity, and disks are harder to change compared to, or rings are harder to change compared to disks in terms of inertia, it takes more time for it to stop rolling as fast.
That is an excellent way of putting it. It's not the energy way, but it's the force way, and that works just fine in any conversation that involves justifying your answer. Now, if you want to use the energy method as opposed to the force method, the ring has more energy at the same speed as the disk. Because the ring is harder to turn, it's harder to get it up to the same speed. Therefore, when it gets on the ramp, it's going to go higher because it has more energy. So either explanation will do. I think we need another practice. Do you think we need? I think we need some more practice. You ready for another one? I have another one. That's ugly. Mr. Shelton, do better. Do you remember these problems about the car going up the hill and the car going into the dip? We had to figure out how fast could it travel without losing contact with the road. Do you remember those problems? Let's assume there's a gentle transition. And let's assume I'm traveling this way with a velocity of, let's go with something slower, 3 meters per second. And let's say the top of the hill is 1 meter above the ground. Could you use this to figure out how fast we're going when we reach here? Try this tonight. Well, probably not. Get a good night's sleep tonight. You have the SAT in the morning.